Welcome back. This is the second part of our section on microtubules. We're going to look a little bit at the dynamics of microtubule formation in this video. So microtubules are nucleated. That means their synthesis is initiated at something called the gamma tubulin ring complex, and it's also called the gamma Turk. And you can see that down here in this bottom image. These red proteins down here are gamma tubulin, and they form something called the gamma tubulin ring complex, or the gamma Turk. Up here in red, you can see a microscopic image where the gamma Turk, the gamma tubulin, has been fluorescently labeled in red, and then the microtubules are labeled due to the alpha and beta tubulin being fluorescently labeled green, and so the microtubule is in green. And so the gamma tubulin ring complex here initiates this microtubule, and then growth by the addition of alpha and beta tubulin will be onto the plus end. Now you can get loss from the minus end down here, and we'll look at that in a moment. So the negative end, the minus end down here, is the gamma tubulin ring complex end, or just the gamma tubulin end, and then the plus end is this free end that's going to grow towards the cell periphery away from the Turk nucleation site. So microtubules form by the reversible polymerization of the alpha-beta tubulin dimers in the presence of the nucleotide guanosine triphosphate GTP and the divalent cation magnesium. The dimers aggregate into these structures called oligomers. Those are effectively little seeds which can serve as nucleating sites from which new microtubules can grow. So that process is called nucleation, and then the process of adding alpha and beta tubulins to either the minus end or the plus end is called the elongation phase. So we have a lag phase during which seeding occurs, and then we have an elongation phase where we have growth of the microtubules. Microtubule formation is initially slow during this lag phase because the process of nucleation is slow. Now, you can accelerate nucleation and effectively eliminate the lag phase simply by the addition of gamma tubulin. So gamma tubulin, when present, can effectively eliminate lag phase so that you just go straight into the much more rapid elongation phase. When you get a microtubule, when a mass of a microtubule reaches a point, or the mass of microtubules in cells reaches a point where the amount of free tubulin dimers, the alpha-beta dimers, are diminished, the assembly then of the microtubules is balanced by disassembly. And so that then is called the Plateau Phase. So there are concentrations of alpha and beta tubulin, and there are masses or numbers of microtubules, and the balance between the two determines whether you'll get plateau or shrinkage, or whether you'll get active growth of the microtubules. So microtubule assembly in vitro, if you do this in test tubes, depends on the concentration, the free concentration of alpha beta tubulin dimers. And so the tubulin concentration at which microtubule assembly, that's growth phase, the microtubule assembly is exactly balanced by disassembly. So when you've got addition of alpha beta tubulin and you've got loss of alpha beta tubulin, that concentration of tubulin is called the critical concentration. So microtubules grow when the tubulin concentration, when I keep saying tubulin, I mean the alpha tubulin dimers, and that will always be the case unless I'm specifying one or the other. So microtubules are going to grow when the tubulin concentration exceeds the critical concentration, and if it's below the critical concentration, you're going to get shrinkage. So you're going to get loss from one or both ends of the microtubule, and the microtubule will shrink. So that's a little bit about the dynamics. Let's look at a phenomena called treadmilling. Now, before we look at the treadmilling business, the negative end and the positive end have different critical concentrations for tubulin. So that means that you can have one concentration of tubulin in the cell, and it will affect the negative end, the minus end, differently than the plus end. So if the critical concentration of the free tubulin concentration is above the critical concentration from the plus end, but below that for the minus end, is what will happen is we'll get a phenomena called treadmilling. So what will happen then is these tubulin dimers will add to the plus end if the tubulin concentration is above the critical concentration for the plus end. These alpha tubulin, beta tubulin dimers will add to the plus end, and we'll have loss from the negative end as long as the critical concentration or the tubulin concentration is below the critical concentration for the minus end. We'll have loss of the alpha beta tubulin subunits from the minus end, and so what will effectively keep happening is addition to the plus end, loss from the minus end. So if we track these blue alpha beta tubulins, obviously not blue, but if we track these ones that got added at time 0, at time +1, +2, +3, plus whatever, so what we find is these blue alpha beta tubulin dimers will move through the microtubule at a certain rate, which is a function of the tubulin concentration against or as a function of the tubulin concentration relative to the critical concentration at the plus end and at the minus end. And that's a phenomenon called treadmilling. There are a number of drugs which can be used to interfere with microtubules and to affect their polymerization and depolymerization. Colchicine, the top of the list here, that binds to tubulin monomers and inhibits their assembly into microtubules and promotes microtubule disassembly. Vinblastine and vincristine here, and you can see where these organisms, where these drugs come from. Vinblastine and vincristine here are similar, they're related compounds, so they're similar to one another, and you can see that they aggregate tubulin heterodimers, so they cause the heterodimers to stick together, to come together. Nicotazole, where is it on the list? Here it is, second one down. This is a very common lab reagent that's used to study the cell cycle, and so that's a synthetic compound, and that inhibits microtubule assembly. And so if you treat cells with nicotazole, they basically arrest in mitosis. So those are a few drugs up there. All of these drugs are called antimitotic drugs because they interfere with the spindle assembly, and they interfere therefore with cell division. Some of them have been used in the past as cancer therapeutics. They're being more phased out now as we get these so-called smart drugs that appear. Some compounds can act to stabilize microtubules. Paclitaxel here, also known as Taxol, that stabilizes the microtubules, and that means that you end up with a depletion of free tubulin because all the tubulin ends up in the microtubules. And again, that has been used as an anti-cancer treatment, but its use is waning now in favor of other less toxic drugs. Okay, so that's a little bit about the dynamics of microtubules and how you can use different drugs to interfere with microtubule polymerization and depolymerization. I'll be back with part 3 shortly. I'll see you soon.